What's up, guys? Welcome back to another video. Today's video is going to be on AVL trees again, but I'll be showing like a bigger example, and it will just help out basically. Because the previous video for the AVL is just the basic idea. This one I'll be showing like bigger example, bigger LLRR, LRRL cases and stuff like that. So, if you remember, we have so we'll be using this tree as an example, obviously. And I'll basically be doing like the height and the balance factor for this. All right, so remember that the height for the node that you want to know, so height n is going to be equal to 1 plus the max of either the left or the right. And then for the balance factor, BF, for the node, it will be the height of left minus right. Well, height of left minus right. So H left minus H right. There we go. All right, so just by looking at the trees, we have 1, 5, 7, 10, and 14. These nodes are leaves because they don't have any children, or technically it would just, their children would be like null. But yeah, they have none. So if we want to find the height for these, it's very obvious. The max for, let's say, node 1, left and right, they're both 0. So max of 0 and 0 will be 0. 0 plus 1 equals 1. So all of these nodes' height will be 1. Actually, yeah. Do this, and then I'll probably change the color for other heights. But these heights is equal to 1. Now, let's look at the balance factor. So we want to find out, obviously, the height of left and right. They're all 0, so the balance factor will be 0. So BF equals 0. So there's that. Now let's look at the next node, which is node 2. So the node 2 has a left child, which is 1, with the height of 1, and a right child, which is null because there's nothing there. And for that, it'll be height of 0. So what we want to find is the height for node 2. So let's put height node 2 in here. And then that's going to be equal to 1 plus the max of the left and right. And then we have a balance factor for 2 as well. And that's going to be the height of left side minus the height of right side. So left side will be 1 because the node 1 has a height of 1, while the right is 0 because it's a null. And then same over here. So when that happens, the height for node 2 will be 1 plus the max between 1 and 0, which is 1. So the height will be 2. And then for the BF, the balance factor, it'll be, again, 1 minus 0. Which will be plus 1 because it's a positive 1. So, oh yeah, I forgot. So right here, what I want to do is I'm going to write out the balance factor for each of the node. So it'll be 0, 0, 0, 0, 0. And then here we have a plus 1. Perfect. All right, now let's do node 6. So node 6 has a left child, which is 5, and a right child node, which is 7. And both 5 and 7 are also has the height of 1. So when that happens, you want to find the height for node 5, which will be 1 plus the max of 1 and 1, which again, it'll still stay at 2. So for node 2 and node 6, both of their height are 2. And then again, 1 minus 1 for node 5 will become 0. And so for node 6, the balance factor is 0. Now let's look at node 4. So node 4 over here, what we have is node 4's child is node 2 and node 6. And node 2 and 6 both have height of 2, which, by the way, I'll draw a circle. Change this. Height of 2. There we go. All right. So when that happens, we want to put node 4, 1 plus the max of 2 and 2. These are the height for 2 and 6. And so when the max of 2 is 2, so 1 plus 2 is 3. So that means the node 4, the height will be 3. And then for the balance factor of node 4, we look at both the left and the right, which again, it would be just 2 minus 2, which is 0. 2 minus 2, which is 0. So when that happens, the balance factor for node 4 is 0, but the height is 3 for node 4. Okay? Now we have to look at the right side before we end with the root. So once again, I already talked about it. Node 10 and 14, both of them has the height of 1 with the balance factor of 0 because they're leaves. So they have no children, or they have a children, but it's basically pointing at null. Let's look at node 12. So node 12 for the left is 10, which has a height of 1, and the right of 14, which is also the height of 1. So when that happens, we have the height of 12, which is 1 plus the max of 1 and 1. So 1 plus 1 is 2. So node 12, even though it is on a different level, it has a different kind of height, which is 12. And now we want to figure out what the balance factor is, which is just 1 minus 1 for 12. So 1 minus 1 equals 0. So there we go. We have 0 right here. Now that we finished the right side, then we can move on to the final one, which is the root. So what root has for node 8 is that node 8 will be, what's the max for the children of node 8 is 4 and 12. 4 has a height of 3, while the 12 has a height of 2. So 3 and 2. Now the balance factor will also be 3 and 2. So the max of between 3 and 2 is 3. 1 plus 3 is 4. Whereas down here it's 3 minus 2, which is a plus 1. So when that happens, we know that root 8 has a height of 4. And then the balance factor is a plus 1. And that's it. That's basically the gist of like the AVL tree. And this one is a valid one because all the balance factor are between -1, 0, and +1. All right. Let's do a bigger example on the left and those like cases, rotation cases basically. And I'm going to just draw it out like a slightly bigger case just to show you an example. So like this. There we go. All right, so now let's figure out the height and the balance factor. So what we want to do is right here, we look at node 5. And because node 5 is a leaf, the height is 1, balance factor is 0. And then, you know, it's going to be the same thing as long as you use this. And so for the height, node 10 is 2, height for node 20 is 3, height for node 30 is 4, and then the height for node 40 is 1. Also, again, balance factor of 0. Now we figure out the balance factor for node 10. Left has a 1, and then the right has a height of 0, basically. So 1 minus 0 will be +1. So we have a +1 here. 0, 0. And then let's look at node 20. Node 20 has a height on the left side of 2, but the right side is 0 because it's pointing at null. And so 2 minus 0 will be +2, meaning we have an error here, which is node 20. That's a +2 right there. And so right there is where we basically say, okay, there seems to be a problem and we need to fix that. So what we do is we just look at it. This is a left and a left case. Left, left. So when that happens, we do a right rotation, which is like this. Basically, once again, you do like a pulley. You pull the 20 down while the 10 and the 5 goes up. And so it'll look something like this. And then afterward, you insert back the 30 and then the 40. Now, when we double check, now we know that 5, 20, and 40 are leaves with height of 1 and balance factor of 0. The 10 will also be a balance factor of 0. And then the 30 will just have a balance factor of +1. And that's basically fixed. Now, you can kind of say that if we go back, and that's basically it, by the way. But you can go back and say, like, but wait, node 30 also has a balance factor of +2. Do we do node 30 or node 20? Well, in AVL, I think the rule of thumb is going to be you always rotate at the first node when you count from the bottom. That becomes unbalanced, right? So, because when you're doing because when you like I basically did, I was going up. The first node that I see it's unbalanced, I have to fix it immediately before continuing up. So that's kind of like what you have to do. So yeah, whenever the first node you encounter where the balance factor is either +2 or -2, this is where you basically do the rebalance, rotate. And after you rotate, the tree above it can usually become like balanced again automatically. So this is basically the left case. Right case will be exactly the same thing, but just mirrored. All right. So now let's do a different case for example, like the left-right case, right? So I'm gonna be giving out a new node, which is a new example. Sorry, not new node. Node 30, node 10, node 50, node 5, node 20, and then node 25. Okay. So once again, let's just quickly figure out the height of everything and the balance factor. So right here, we have a height of, all the leaves has a height of 1 with a balance factor of 0, because 1 minus 1. And so 0, 0, and 0. And then we're going to change colors. Now let's figure out what node 20 is. Node 20 has a height of 2. With a balance factor of -1. Now, -1 is because the left is null, but the right has a node, and the right is 1, right? So what you do for left minus right will be 0 minus 1, which becomes -1. So the balance factor for node 20 will be -1. And keep in mind, another thing that I can kind of do when it comes to sort of like being able to know what cases I use is I would say that if it's a -1 or +1, -1 I'll call it like left heavy, something like that. And then if it's a -1, so sorry, +1 is left heavy, -1 is right heavy. So for this part, node 20, I would call it right heavy. Or, I can just keep it in my mind, But sometimes writing it down is pretty good too. So erase the heavy part. I'm just going to write right side. And then let's look at node 10, which I'm going to change it to a different color. So node 10 has a height of 3. Once again, you use the equation to figure out the height. And then for the balance factor, same thing. You use that equation, just left minus right. So the left part is a height of 1, while the right part is a height of 2. So 1 minus 2 becomes -1 again. So balance factor is -1. -1 here for this. And once again, this is right heavy again because it's -1. Node 50, we already figured it out. And then let's look at node 30. So far it looks good, but node 30 is definitely the problem. because yeah, I mean, I was one who wrote out the example, so I know it's a problem. But in case let's pretend we don't know, right? So we have a height of 4, and then we're trying to figure out the balance factor for that, which is 3 minus 1, because the height for the left is 3, while the height of the right is 1, which becomes a plus 2. Now we identify the problem. Node 30 is the problem. And this time it's a plus 2, which basically tells you that it's a left heavy. Okay, so now we identify what the problem is. We can basically figure out, we want to know like what case do we use, right? And this is the part where I wrote down like why, like how to basically solve it. Because the problem is that it is left heavy, and then on the next part it's a right heavy. We have to do a left right case. So left right. Going back to this example over here, you can kind of tell that like just by looking at this portion that this is a left heavy into another left heavy. Okay? And you don't look at this and say like this is right heavy problem, because these two nodes, their balance factor is fine. This is the problem. So we have to look at this instead. These two balance factors both have a -1, so they're not out of the -1, 0, and 1 for the AVL. And so that's why we have to look at this part, node 30. And node 30 is a left heavy into a right heavy. So we have to do LR. All right. And then to do the LR case basically is you want to look down on the node below it to do first the left rotation case. And so what we do here is, let me go up here and just separate it real quick. We want to do this whole section first, the left subtree. So right here, we have what, 10 into 5 into 20 into 25. So we want to do a left rotation, which is this direction. And so once again, think of it as like a pulley. You want to pull the 20 up here with the 10 down here, and then the 5 down here, and then the 25 here. Okay? So that completes the left part of the rotation. So this part is done. Now we want to do a right rotation. And let's just add back up. Oops, not this one. Once this part is done, it's fine. Let's just add this part up. And then with the 50 here, you can kind of see that we're doing a right rotation, because right here, it seems that this is a very left side heavy, and this seems to be looking like a LL case. And for an LL case, you have to do a right rotation. And so when that happens, you're basically confirming that, yes, this part is indeed a left-right rotation case, or left-right case, and then you have to do the LR rotation. And so now we can do the right rotation. And for the right rotation, we're gonna first, let's just pretend that the node 25 isn't there, and we're gonna do a right rotation like this. And so 20 becomes here, whereas the 30 is here, and then the 50 is here. So once again, it looks like a pulley, 10 and 5, like that. Now, how exactly do I sort of like add the 25 back, right? You want to know that like, because there's two things that must be like basically preserved. It's that the binary search tree ordering has to still be where like the left subtree of the node on the left subtree are all values less than the root value over here, which is 20. And then so the search order is still going to be correct, right? Which will be 5, 10, 20, 25, 30, and 50. So that this way the order are still going to be like the in order traversal of the subtree. And so in a way, it's sort of like when we create that, now the root, the node 20 is now the root, and that the 30 is still on the right side while the 50 remains on the right side again, where exactly do we put, like, do we put a node here, and what node do we put here? We can kind of already know that node 10 is here, and it fills up the gap. But what about like node 30? Well, that's where the node 25 comes in, because node 25 is bigger than 20, but it is still less than 30. And so what, in order to sort of like understand, hey, where do I plug in this node 25? Well, you know, just by doing a basic binary tree, just by thinking about it, you can kind of tell that like this is where I should put it, and not put somewhere like here, because then it wouldn't make any sense and it would just be unbalancing the tree again. So hopefully that makes sense. But the final result of the tree should look something like this. 10 and 5. And now when you do the height and the balance factor and everything should, all the balance factors should be remaining within the -1, 0, and +1. Okay, so that's basically the left-right case. Once again, just like I said with the left-left case, if you want to do a right-left case, it would just be the mirror side, and you just do the exact same step, and then just get the right solution. But yeah, that's basically it. Long video, had to do some editing, but thanks for watching, guys. Bye. If you want to see another side of me that isn't always about computer science, then check out my other YouTube channel and come and watch my Twitch, where I play a bunch of competitive games either by myself or with my friends. And not only that, but I do have my Discord available just in case if you wanted to add me, either to just talk about anything, whatever you want, or have some kind of question from my video. Thanks.